down on one particular part of an NVMe, which is called I/O determinism. And the main point of I/O determinism is to get predictable latency out of a solid-state storage drive. And I'll talk a little bit about the requirements that are coming from the hyperscalers, some of the concepts, a little bit more detail than Jay covered, and actually this new way of actually sort of dealing with an SSD to try and get these predictable latency results. So I used the wrong color because you can't see it here. It says legacy mindset, and it's usually sort of vertically scaled in a legacy situation. You have a worker that's doing a number of steps that sometimes may depend upon the previous step and so forth. But to speed that up, what the hyperscalers and modern computer architecture are doing is they're scaling out. They're trying to divide their tasks up into many little parallel tasks in an effort to accomplish the same thing much faster, scale it out instead of scaling it vertically. But the problem comes in when you get one of the steps takes 10 times as long to perform. And why does it take 10 times as long to perform? It's usually because of the SSD. And it's actually worse than that because there are multiple steps, all of which then end up in parallel. And it's the longest path through all of these that ends up actually showing up to the user space. So we really want to be able to get predictable latency in the operations that we're doing. So this, you can start to see here, is a graph of how often or what chance of getting this much latency, right? 100 microseconds, 1,000 microseconds, 10,000 microseconds. And what we see is that you get some program collisions, and then for a certain number of, these, you're going to start to get erase conditions and so forth. So I/O determinism is the idea that you're going to limit and possibly eliminate these long tails, so the tails that are way out there on the latency curve. And there's a couple of reasons. One is the noisy neighbor that Jay talked about is when you have multiple processes coming in and interfering with each other in trying to get a good latency out of the drive. And this is getting worse. As drives get bigger, 30 terabyte drives, how many apps do you have to point at that same drive and to actually utilize the performance and capacity that are there? And then the other classic issue with SSDs is the background tasks, right? All of a sudden, I have to do read patrol. All of a sudden, I have to garbage collect, and that interferes with the latency as well. So the first concept we came up with is to isolate the raw capacity into individual miniature SSDs called NVM sets. And then the second concept is hold off those background tasks and create a special window in which only reads are done and no background tasks are allowed to run, right? So there's one more kind of trick that we threw in here, and that's called fast fail. And because the host is keeping multiple copies of the data in multiple places on multiple SSDs, if it looks like you're going to throw a long tail, if it looks like you're going to have to do some, threshold voltage modification or ECC correction or, RAID kind of recovery, give up. Give up in a matter of microseconds, not taking 10 milliseconds to figure out what the data, where you're not going to be able to get the data down. So you fail fast, host finds it somewhere else, faster than it would be if you tried to recover it. But this is going to require new behavior on the host. And if you're programming against NVMe drives, you want to get this tail latency out of there, you're going to have to do some things differently. So the typical architecture in today's SSD drives is all driven around trying to get bandwidth. And we thought this was a good idea. We want 1 million IOPS, right? So we actually, inside the drives, try and use as many channels and as many dies as possible to store the data in parallel so that the throughput could be really good. And that's great. But then you have 30 different applications trying to hit the same drive. It's not so great. So we're really trying to get to a place instead where you can take some of the dies here and dedicate them to one app, and some more dies and dedicate them to a different app, and then isolate the I/O in those cases so that the apps don't interfere with each other. When they need to do some writing, they would do the windowing into a write mode, and we call non-deterministic. So the first concept is NVM sets. It is basically like a miniature SSD. The idea being that you might take the channels that are hitting all your dies, and that would be one NVM set, and you have another channel, a couple channels, that would be another NVM set, and so forth. Different hyperscalers, different customers will have different requirements, but anywhere from 0.5 terabyte to 1 terabyte is kind of the size they're thinking about. And you can see this from the way they put together their systems, trying to get as many of these little M2 devices into their system as they can, like an OCP Lightning, for example. So here's it graphically illustrated here. You have set A, B, and C, and then you can carve namespaces out of that set. What's not allowed is you cannot have a namespace that bridges set, because you got dedicated channels here and die, dedicated channels here and die. So if you want to do that, you do it outside the device. So within a set, you can create these namespaces. When a host creates a namespace using the namespace management command, now you have to specify the NVM set identifier. You didn't have to do that before. And then you need to indicate support in the controller attributes field and some of these other endurance groups I'll talk about in a minute. And then for each NVM set, you're going to indicate the associated endurance group. An endurance group is just a way of telling the host how much, sort of on what granularity do I do wear leveling. Do I do wear leveling across the entire drive, even though I'm giving you individual NVM sets? Now it may be put on the host for him to wear level amongst these NVM sets. So if he's bashing a single NVM set all the time, he's going to wear out those underlying die faster than the other ones, right? So he needs to know that that's happening, because he's going to have to balance his loads if his policy is to wear the entire drive out and replace it all at once, right? You'd also just let these individual NVM sets wear out and start using a different one, different policies. So the endurance groups are either one-to-one, there's an endurance group for each NVM sets, or multiple NVM sets could share an endurance group. Or you could have one endurance group for the whole drive and all NVM sets. It becomes a little bit difficult to do that just if you're isolating based on channels and so forth. And here, again, you could do this where you have one endurance group for multiple NVM sets, but I'm going to tell you the architecture we're working on doesn't do that. All right, so I mentioned the fast fail. This is also known as read recovery level in the spec EASE, and it applies to individual NVM sets. You can set the recovery level differently on different sets if the drive allows it, and it indicates support in the controller attributes field. So there's different levels here, and most drives, I would say, at least initially, are going to support 2. They're going to support level 0. Level 0 is the same amount of recovery you do today. The recovery you do today in an SSD is, I really want to get that data, because otherwise the customer is going to think the drive is broken, right? And then level 15 is kind of this new new level, which is the give up quickly. And what I mean when I say give up quickly, it is not a timeout. It's not spec'd as a timeout. It's spec'd as you have some code and it detects some extra step that you're going to have to take before you return that data to the host, right? It could be any sort of recovery at all, but if it takes any amount of time beyond the normal, 20 microseconds, 200 microseconds latency, don't do it. Give up, because the host has another way to get the data. So you don't try with a different threshold voltage. You don't apply ECC correction. You don't apply parity correction. You just fail the command immediately. And that's okay, because the host has put this data elsewhere and likely can get it back a lot faster than you could with your recovery. And this, again, eliminates that long tail. Namespace management. Again, you have to use the NVM set identifier in creating a new namespace. And that's about it. But the really innovative kind of, I think, aspect of this is not the noisy neighbor problem. It's actually getting predictable latency in the face of all the background tasks that the SSD would normally want to do. So that's what, actually IOD is broken into two different TPs, we call them. And this is a dedicated one for predictable latency. So the NVM sets and their associated namespaces have these quality of service. What we really mean is isolation between different NVM sets, right? And these are vendor specific, and but they're isolated by ideally sending commands to different sets, and then read recovery levels as well. So how does this look from an actual application point? There's actually two windows in here. One window of time is while the drive is in the deterministic window. And then the deterministic window is mostly just going to be doing reads. And he's going to expect those reads to come back in a very predictable amount of time, very predictable latency, no long tails. But he knows that the drive is going to accumulate a bunch of work during this process, right? Because I'm not doing garbage collection, I'm not doing read patrol, I'm not doing anything that's going to affect the latency. So you have to give me some time to do all those things inside the SSD. And that's in the non-deterministic window. So I'm going to read, and then I'm going to say, okay, now you can go do your work. And so we have a bunch of indicators that say, while I'm in this mode, I'm building up work. So I'm indicating to you that you're running out of reads, you're running out of writes, and you're running out of time. And once I get into the non-deterministic window, then I take those values and build them back up so I can go back into the next deterministic window. All right? So this periodic, use it for reading, use a period for writing. That's this whole windowing thing that predictable latency enables. So the deterministic window is a window of operation during which the NVM set is able to provide deterministic latency for read and perhaps a few write operations. Not much, right? The non-deterministic window is a window of operation during which the NVM set is not able to provide deterministic latency for read and write operations as a result of preparing for a subsequent deterministic window. In other words, working off my queue. Some examples include repair and background operations. We didn't really want to get too specific in the actual specification. And so you configure which window you're in the predictable latency mode window feature. Now, as I mentioned before, this means your code in using one of these drives has to change a little bit, right? When you create an NVM namespace, you have to supply which NVM set ID you want in it, and so forth. So deterministic excursion is when the host kind of ignored the rules, or there's some exceptional condition, right? I got a bad block, I have to rewrite data, I got a read disturb. Any number of those things could happen. And right now, I have to give up on that sort of deterministic read guarantee and go off and do something to protect the data. So at any particular time, the drive could do this excursion, but it should be very rare. And you could take measures inside your SSD firmware to do that. So what does it mean to be well behaved? You know, the host needs to either, on the basis of time, he knows how long he can spend in a deterministic window, or on the basis of these parameters that are decrementing or expiring. And then he can, for reads and writes and time in that deterministic, we have the typical amount of time that the attribute may consume during any given deterministic window, and a reliable estimate of the amount of that attribute that remains to be consumed during the current DT win. So this is what it would look like with those parameters. This is the number of reads you can do in the deterministic window. And you start off in the deterministic window and the number of reads decreases, right? And then you switch to a non-deterministic window and those build back up again. But maybe not all the way back up to the previous one. So that decreases over time and then increases and comes back up. Same with the writes, and this might be a much lower number. Maybe you only can do enough writes to fill up a write buffer. And then the DT window time is sort of inversely proportioned. This is the maximum amount of time you could possibly spend in the window, deterministic window, without having to do something like read patrols. So that starts off at this value, decreases down, and then you can build it back up into the maximum time. These are all indicators that the host doesn't have to look at. He could just use it based on time and do the switching, you know, orchestrate several drives together. And that's what's meant by the controlling the windowing. The host actually sets a property that says, I'm switching you to this mode or this mode. And that estimates can be used if they want or not. Some of the folks we talked to said they're not going to use those estimates, even though we went through 9 months of debating these efforts in the standards group. And then the time-based parameters I just mentioned as well. And then the transitions. At what point may the drive transition, and what point should the host transition? And these are the DT win reads estimate, DT win write estimate, and DT win time estimate. And when we say reliable estimates, it's really up to you to figure out for your drive how you best implement these, right? What is the algorithm for the actual numbers that you put in this? It's up to you. We didn't want to get too specific in the host. We wanted the innovation to happen in a vendor-specific way. So that's why this stuff is kind of vague at the front. But if you have trouble when you're starting to implement this, you know, send me an email. I'd be happy to step you through it. Okay, so this is the orchestration I was talking about, right? Let's say that the host has 3 different sets on, typically it would be 3 different drives. They might even be geographically separated for some reason. Maybe you don't want the data center to take out all your data. So, so this is the orchestration I was telling you about. The first NVM set is placed in deterministic window. And about the time that he's going to have to switch to non-deterministic window, he's got this one already in the deterministic window. And so he could switch and start to reading from the data from here. When that one runs out of time, he could switch to reading from there, switch back up. So you can see at any given point in time, there's at least one of these NVM sets that is in the deterministic window. And even if you draw lines like this, you can find quite a few places where there's 2 of these in deterministic window at the same time. So you can do a sort of a ping pong or parallel fetch and get double the throughput that you would normally do. Now, what happens when you want to write? Well, that needs to be done in non-deterministic window typically. So you would put one in a non-deterministic window and do your writes of the next object, let's say, multiple blocks, right? Okay, I finished writing, now I can put it back in deterministic window. Next one, well, I haven't written that object to this set yet, so I have to put it in the non-deterministic window and write to that one as well, this one and write one. Now that object is in all three of these NVM sets and can be fetched from any of the available non-deterministic windows. Does this make sense? Well, this is how the scheduling would work. Now, 3 full copies of the data is not a very realistic thing as well, right? So almost everybody's going to do some sort of sharding and erasure coding. But if you use a scheme where a third of your drives are in the deterministic window at any given time, you could do the same sort of thing, right? It all depends upon the scheme that you use for your sharding, how many pieces of data are actual data, and how much is actually parity information. So data set applications, the truth is they're always reading, they're always writing. You got multiple producers and consumers on the same SSD, but with the right infrastructure changes, those data center customers should be able to almost eliminate these long tails of latency. And that's really what they were trying to fix when they went and proposed the open channel stuff, okay? They thought, well, gee, I'm going to have to take over the whole control of the drive in order to eliminate these long tails. But 2 years ago, Facebook, Google, Microsoft Azure, and even Amazon came to the NVMe board and said, look, we know you want to protect the value you've put down into your SSD firmware, your markets, everything else, your ecosystem. We really don't want to destroy all that. But we will if you don't create a standard that works for us. So that's what we did.